So Unit 5, we started to transition from forces and, describing how and why things move to, really what do those forces do to an object. So the first concept that we looked at was this idea of work. And really, whenever work is done on an object, energy is transferred to that object, right? So how does that relate to forces? Well, when we do work on an object, we are going to exert a force, and by exerting a force, we then move the object some distance, and move the object a distance, right? Or we displace the object, right? So if I have an object here and I apply a force to it, the object will eventually move over here and it will have gone some distance d. So one way of quantifying work is to relate this force and the displacement of the object. So work is said to be force times displacement, and it's actually only the force that's in the same direction as the displacement. So we put a little cosine theta there in case, say, our force were to come in at some sort of angle. We would only use the component that goes along with the displacement of the object. Right? Now, as we do work on an object, so we apply a force and it moves some distance, we have added energy to that object. Work adds energy to objects, right? So if you want to ask yourself if work is being done, ask yourself if the object's energy is changing. So then we have to go and look at, okay, well, what kinds of energy are we talking about? So there's lots of different kinds of mechanical energy, and I'll go through them one by one and kind of explain how they relate to work as well. So mechanical energy, the first type that we learned about was gravitational potential energy. So gravitational potential energy. And any potential energy is energy that is stored within an object. And the generic variable that we use for potential energy is the letter U. So this could be U gravitational, this could be U electrical. There's all sorts of different types of potential energy. U elastic. So U is a generic variable for gravitational or for potential energy. But typically when we started learning about gravitational potential energy, we used this GPE as an abbreviation for the concept. So if I were to apply a force and I were to say pick an object up from the ground, so I lean down and I pick it up, this is perfect drawing, and I move it up into the air, right? Now it is up here, it's taken some force to move it up there, and now it has stored energy in that object and the potential for that object to fall to the ground. So the stored energy in this thing is gravitational potential energy, which is equivalent to the mass times gravity times the height. And really this is the change in height, right? So how much did I move it up? Right? Now, typically within a system, what I'm going to do is I'm going to define the lowest relative position within that system as being the height is equal to 0, so that the change in h would also be equal to h. If I wanted to graph this, a lot of times we'll look and see, okay, well, what is the relationship between the energy stored in the object and maybe the height that the object or the distance that it is moved. This is a linear relationship. So a lot of times we'll see GPE on this axis or U, remember it can be U, and then we would have height on this axis, and we're going to see some sort of linear relationship. Now, we also have another type of stored energy, and this type of stored energy relates to things that are elastic, so springs, and anything that has any sort of elastic property to it. Springs are the easiest to quantify, so they're typically the ones that we look at when we deal with elastic potential energy, but anything that has any sort of elastic property is going to have elastic potential energy. So elastic potential energy is equal to 1/2 kx squared. So this is when we have a spring. So springs have some natural length to them. So this is sort of like the normal shape of that spring. And if I were to come along and I were to grab onto this box and I were to pull it, or I were to push, right, I'm exerting a force and I would move this thing some distance, right? So let's say I pulled it out in this direction and I displaced it by some amount x, right? So this is I have stored now elastic potential energy into this object because I've pulled it out. If I were to release it, it would shoot back in the other direction. So there's some stored potential here. So my variables here are x. Really, this is the change in length of the spring from any position. Like if I were to move it here and then I were to move it from here to here, I could figure out the amount of energy added just in this change in x, or the total energy in the spring and this total change in x, right? And then k, which is the spring constant. And the spring constant is basically how springy your spring is, and the unit for spring constant is newtons per meter. It's how much force it requires to move a spring by 1 meter. All right, and then the other kind of mechanical energy we talked about in this unit was kinetic energy. So kinetic energy is the energy of motion, and so the energy things have as a result of moving, and that that equation is 1/2 mv squared, where m is the mass and v is the velocity of the object at any moment, right? Now, if we look at both of these things graphically, we have not a linear relationship, but we have a curve relationship relative to the velocity in the x. K is typically a property of the spring, so that's not going to change throughout the duration of your experiment. It's a constant usually. And typically your mass doesn't change as you're moving around. That's not necessarily true. Things mass can change, but for the most part, we're dealing with things that are going to have a pretty consistent mass. So the variable we typically look at is velocity in this case. So if we're going to plot the elastic potential energy versus the x, or the displacement of the spring, this is a curve relationship, or the kinetic energy versus the velocity. This would be a curve relationship. Right? All right, so those are 3 types of mechanical energy. We have gravitational potential energy, elastic potential energy, and kinetic energy. Now, there are other types of energy that are not considered mechanical, like thermal energy or electric potential energy, that can come into consideration when we're dealing with the idea of what is conservation of energy, right? So energy is always conserved. It can only change forms. It's never created or destroyed, right? However, when we're talking about mechanical energy, unless the system is completely isolated, mechanical energy isn't necessarily always conserved, right? But if we're ignoring friction and any sort of external factors, we can say that energy is conserved within a mechanical system. But again, remember, if there ever is some sort of loss of energy, it is because of like friction or the loss of thermal energy. All right. So when we deal with conservation of energy, it's always energy going from one kind of thing to another. So if we use the idea of something having some sort of stored gravitational potential energy and then we drop it to the ground, it starts to go faster and faster and faster, and so it gains kinetic energy. So there's a swap between gravitational potential energy and kinetic energy. If we use the idea of a mass spring system, all of a sudden you have a spring, and you stretched it out, you release it, it's going to shoot back in this direction and start to gain kinetic energy, right? So really the key to any conservation of energy problem is set the energies before equal to the energies at some other point, like after within the system. So if I wanted to know like what solve something about energy right here, we would just set this as my like beginning and this is my after, and just say, okay, what kind of energies does it have here? Well, there it only has gravitational potential energy. But when it's here, it has some height above the ground and also has some kinetic energy as well, so it must be equal to the GPE and KE that it has there, right? Same thing with a mass spring system. So if we have something going back and forth and oscillating like this, if we extend it out, we have stored elastic potential energy in here and a gradually becomes kinetic energy as we go in this direction. So we can pick any relative position in here and set the like here as point 1, and here as point 2, or here as point before, and here as point after, and set those two values equal to each other to solve for anything. Okay, so we then mentioned sort of right after we talked about energy, the idea of power. So power, and I'm not going to go too much into detail about this. So power is either the rate of work transfer or the rate of energy transfer. So it's work over time or energy over time. And either one of these is equivalent. And then we've also derived several times this equation, force times velocity. Let's talk about units for a second. So I haven't really mentioned, but power is watts for units, which is the same as joules per second, because the unit for energy and work is joule. All right, so now let's go ahead and start to, actually I'm going to cut it off here so that I can start another video, and we'll talk about the second half of this unit, which was momentum and impulse.